do a test, and then continue class. Okay? So, with that said, let's get started so we don't have to play catch up later. So this section here is actually sort of a catch up section. There's no real new material in this section. We're just going to look at some of the applications of the derivative, specifically as we think of it as a rate of change. So one thing I'm going to do is differentiate between words that sometimes are used interchangeably in English, but in mathematics and physics we need to use them separately. Okay? And then we'll start looking at some applications. So the first thing I want to say is let's go ahead and define the word displacement. Okay? So the displacement can be thought of as the final position minus the initial position. Yeah, it's like the change. It's the change in the position. So generally, if I ask for the displacement at a certain time period, it'll be where is it, or how far did it move from when time between the current time and when time equals 0. Okay. So oftentimes this initial position will be at t0.
So is it the same as the f of x plus h minus f of x, kind of?
Not necessarily. Not necessarily. It would be like f of b minus f of a if f measured position. It doesn't have to necessarily be a very tiny displacement.
Okay.
Yeah, great question. So then distance then is equal to the absolute value of the displacement. Okay? So let me just say this another way. Displacement is a vector, while distance is a scalar. So we're not going to talk about vectors per se in this class. That's a topic for another class. But what I want to say is that displacement has both a numerical value, okay, called a scalar. It has both a value and a direction. So for example, if I tell you the displacement was -3, then we know that the displacement, we're displaced 3 units to the left of 0. So there's an orientation there with that negative number. But distance would just be 3. So for example, let's just say that we started moving from, say, Denver. Okay, at Denver is at mile marker 0. Okay, we're going to make it for our own mile markers for this highway. Okay, so at mile marker 0, we're at Denver. If I went to the north up, say, 40 miles, maybe I ended up at Fort Collins, which is over here, at a displacement of 40 units to the right of Denver. Okay, and say I went 40 units south, then I'd end up somewhere here at mile marker -40. And I don't know, let's just pretend, I know this isn't quite right, but let's pretend that's Castle Rock. Okay? So notice that both Fort Collins and Castle Rock are a distance of 40 miles from Denver, but the displacement for Fort Collins is a +40. The displacement for Castle Rock is a -40. Okay? So we will take care to make a distinction between distance and displacement. I'm never going to purposely try to trip you up, but later on I might ask the question, if I start here, walk this way, then walk this way, then come back, I could ask you what was my net displacement, but I could also then ask you what was my net distance. The net displacement would be how far I am from where I started, but my net distance would be as if I had a pedometer on or a watch or something that was marking how far I traveled. So you see those are two different questions, and they do provide two different bits of information. So we do want to start distinguishing between those two. Okay? So like I said, I'm not going to try to trick you on these. I know I could ask some tricky questions. I'm not going to try to trick you on these. But we will make a distinction between the two, and it will be important that you realize the difference between the two. Well, velocity then is final position minus initial position all over final time minus initial time. Okay. Let's look at the units on that. That would be units of position. So let me just make that up. That would be something like meters per second or miles per hour or something like that. That would give us the units on velocity. Okay. So again, that's final position minus initial position all over final time minus initial time. Okay. Where, so this would be our velocity, where our speed is simply the absolute value of our velocity. Okay. So again, using that same terminology, speed has both a magnitude and, velocity has both a magnitude and a direction. I am heading 30 miles per hour north. That is different than heading 30 miles per hour south. But if I ask the speed, in either case, the speed would be 30 miles per hour. Okay? So speed has just a magnitude, distance has just a magnitude. Okay. So let's look at this example here. I'm not going to spend a whole lot of time on it. We've got a patrol car that leaves the police station at noon. So at noon, the patrol car leaves the police station, heading east. Okay. Now, his or her position is given by this function s here. Okay. And if s is positive, we're going to say that you're heading east. And if s is negative, then we're going to say that you're, if s is positive, then we're going to say that your displacement is to the east. And if s is negative, then we're going to say your displacement is to the west. Okay. By the way, for those of you who don't know, here's a nice little compass: north, south, east, west. Okay. So east is usually oriented with the positive direction because that's to the right, just as north usually is when we do physics problems. Okay. That's just customary. We could choose to call west a positive value, and then east would be a negative value. But we have to pick one, and so we tend to do a left-right orientation to these. Okay. So here we're asked to describe the location of the patrol car during the first 3.5 hours of the trip. So I would say that the patrol car starts off heading east for about an hour and a half, arriving at a position 80 miles east of the police station. And then what's happening between time 1.5 and time 2? Yeah, between 1:30 and 2 o'clock p.m., this car's displacement is not changing, right? So what's the car doing? It's standing still, okay? Looking for the opportunity to catch a speeder or something, okay? So then the car starts at time 2 o'clock, starts decreasing the displacement, right? The displacement is decreasing. What does that mean?
Heading back to the station.
The car is heading west, returning back to the station. Okay? Until, I don't know where that is, probably about 3:15, the cop car passes the police station, but then continues on, right? It doesn't stop there because the displacement never remains the same for any period of time, right? Doesn't stop there, continues on past it, and at 3:30 p.m. is 20 miles to the west of the police station. Okay. Anyone want to go over that further? I'm not necessarily looking for a right answer here. I mean, that was about 2 paragraphs worth of information I just gave you. Okay. But could you describe this behavior? Yes?
Is this a standard way to describe behaviors of where things are going?
Yeah. Yeah. So
Is this the most intuitive way you think? It's just I mean, I'm brand new to this, thing, but I'm just like, we're going this way up, but that means he actually went left, or we're still going right.
okay. So
I was just like, is this the most intuitive way to calculate that?
Well, so notice what we don't have here. Like, we're not showing. So this axis right here is not east-west. This is not the east-west axis. This is time passing, right?
Right.
So this is as time is passing, what is happening to the displacement. If the displacement is becoming positive, we said that that means that we are going. That means we are to the east of the station. So.
No, I totally get that.
Yeah. So are there other ways to do it? Yes. Another way to do this would be to do this in just one dimension. So this is a two-dimensional graph representing what's happening. If we did it in just one dimension, here we could have, here's 0, okay, and here's, heading east, and we would draw the behavior so it looks like this. Okay? But the problem is that doesn't really convey the element of time that's happening here. So I could put some time values on here, like right here is at t equals 1.5, but it also is at t equals 2, right? And then right here is t equals 3.15. What am I doing though? I'm adding more dimension, I'm adding more information to this graph, so I'm actually making it a two-dimensional graph. Okay? But that gets pretty cluttered, right? Because you can't tell, for instance, from what we've learned, the steeper your tangent line, the faster you're moving. You can't really see how quickly time is passing along here. Now, if I could put a little dot and you could watch it, if it's moving quickly, that means the car is moving quickly, and if it's going slowly, then the car is going slow, and if it's paused, then the car is rest. So if you could watch a dot move along this in some way, speeding up, slowing down, pause, going this way, speeding up, constant distance, if you could watch a dot move along there, then that would very accurately represent what's happening, but that is hard to graph on paper. You need computer to represent that. Yeah. So by the way, this is two-dimensional. This is a two-dimensional representation of this one-dimensional problem. Okay? If I were to just draw the curve along here, this type of motion going back and forth along a line is called rectilinear motion. We'll talk about that on the next page. Okay. Here we're asked to find the displacement and average velocity of the car between 2 p.m. and 3:30 p.m. Okay. So what is the displacement? So we said the displacement is the final position minus the initial position. So what is the final position at t equals 3:30? I think that's at -20, correct? Which means we are 20 miles west of the patrol station. And the initial position was at 80. So our our displacement is -100 miles. What does that minus mean? It means we were displaced to the left of where we started. We didn't drive -100 miles. Our distance that we traveled wasn't -100 miles, but our displacement is -100. Where our average velocity would be that -100 miles over the length of time it took to do that, which was 1.5 hours. So our average velocity was approximately -66.7 miles per hour. Why is it negative? Because it's velocity. That negative refers to driving in which direction? Driving east. Okay? Notice that the average velocity is basically always -67 miles per hour, even though sometimes we are currently east of the station. Okay? And it's not until after 3:15 that we're actually to the west of the station, but we're always heading in that negative direction, in that westwardly direction.
So, I'm
Yep.
sorry, can you repeat? It's -66.7 miles per hour to the east.
Well, so you can't. So you have to pick one or the other. So you either say that he's traveling at -66.7 miles per hour, or you could say that, and this is more intuitive, 66.7 miles per hour to the, and I said east, I think initially, I meant to say west.
Oh, okay, that's what confused me.
Yeah, sorry about that. But notice you can't put negative and to the west, right? So this is like if you go to Las Vegas and you lose all your money, you either say I lost $100 or I came out with negative $100, but you would never say I lost negative $100, right? Does that make sense? Okay. So you could either say I was traveling negative 66.7 miles per hour, or I was traveling 66.7 miles per hour to the west, but you couldn't put a negative in front of that. Okay. Great. At which times was the instantaneous velocity the greatest? Well, it seems to me that sort of anywhere between here and here, we have the tangent line looks like that, and that's the steepest the tangent line ever gets. So it appears between 12:30 and 1 o'clock p.m. There was a question, I saw a hand.
Yeah.
Yep.
Isn't the derivative of the velocity function at 0 where the highest point?
Well, careful. This isn't the velocity, though. This is the position.
Mm-hmm.
So in fact, the velocity of the car, where the displacement is the greatest in this case, happens to be 0. The car's at rest.
Right.
But where is the velocity the greatest? Well, that would be the derivative of the position function. So we're looking for where this. So that's actually a question about the second derivative. It's like where would. So maybe that's what you meant.
That's what I was.
Where does the acceleration have a maximum? And that would be true.
Yeah.
But we haven't quite gotten there yet. Great questions. Okay. Flip over to the next page. All right. So again, this is going to be, we're going to represent this one-dimensional idea in 2 dimensions, which is a little bit confusing. Okay, so I use this phrase rectilinear motion. Okay. What is this object going to do? It's going to move horizontally along a line. It's either going to be moving to the right or to the left, or staying put. Okay. We say that if it's to the right, then we'll say S of t is positive. Okay, and that's common. That's we always pick to the right as positive. Okay.
This is kind of like that question on the exam review where it was saying the spring was moving left and right.
Bingo. This is exactly like that spring question on the exam review, except this isn't necessarily a spring in this case. Yeah, great. And in this case, I'm going to just consider the model between t equals 0 and t equals 6 seconds. Okay. All right. So my other class, we had to graph these, but I graphed them for you just to save some time because we got less time tonight. Okay. So here is the displacement function. Folks, I don't think it would be unfair to ask you to graph this function. Could you graph it? Okay. So it's a cubic, right? And if you want to know where it crosses the x-axis, you'd go ahead and factor it. So that'd be t times t minus 5 times t plus 3. So its zeros are at t equals 0. Again at t equals minus 3. And over here at t equals 5. Those are the 3 zeros. Yeah?
So, I mean, we could get like a general sketch of it. Are you saying we would need to graph it exactly where the points should actually be?
Well, I think you should
You know
get
what I'm saying?
these. Yes, I do. I think you should get these from college algebra. I think you should get the long-term behavior from college algebra. Now, where exactly are these turning points? I think you should be able to get those, but maybe not on a first pass. Okay?
Now we just find the derivative of those points.
Well, let's see here. Where does this thing? Let's answer that question. Let's answer that. Let's answer Keegan's question. Where does this have a? Where does this turn around? Well, where it turns around, it also has a what? Horizontal tangent line, right? What does it mean to have a horizontal tangent line? It means its derivative would be what? 0. So if I take the derivative of this function, s prime of t, that would be equal to 3t squared minus 4t minus 15. And I could factor that as 3t and t and, let's see here, minus 3 and plus 5. That's how that factors. And so down here, I've actually graphed the derivative of this function, the velocity curve. And notice the velocity curve has zeros at t equals 3 and at t equals minus 5/3. I could find that simply by taking the first derivative and setting the first derivative equal to 0 and finding the x-intercepts of this. Folks, I want to make sure that part makes sense. Okay. I could find where the first derivative is equal to 0 by taking the first derivative, setting it equal to 0. This tells me where the derivative is 0, but that also tells me where this original function has horizontal tangent lines. So now I know that I've got a turning point where? At t equals what?
5 over 3.
At t equals minus 5 over 3, and at t equals 3. Then could I find the actual y value of the function there? Yeah, I just plug 3 into the original function, and if you plug 3 into the original function, you get the order pair 3 comma, I think, 36. So now I know where that turning point is. Thank you, negative 36. Okay, does everyone see how I did that? Please, 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 I know you're tired from the test, but I want to make sure you understand how I just did that. Anybody want to talk about it?
So where did the 36 come from?
Yeah. So I know that, so we understand where the 3 came from. That was where the first derivative was 0. Okay? If I want to find a y value on a function, what do? Plug 3 where? Into the original function. So if I plug 3 into the original function, 27 minus 18 minus 45 gives me negative 36 when you add those together. Great, good question. So yes, I think you could graph this whole polynomial function in this case, because you could find where you have horizontal tangent lines and then plug them into the function, okay, and then go ahead and evaluate it. By the way, this one right here, if you're interested, you can check me, but this is the order pair negative 5/3, comma 427ths. That one's not very nice, but there's a lot of nice points on this graph, so.
Is this foreshadowing? Are you saying we're going to need to graph stuff?
We're going to spend more time focusing on how to graph, but I feel like we're going to have 2 sections just on how to graph functions using derivatives. But I feel like this part isn't, I'm not really spoiling anything that you haven't seen before. Okay? Although I maybe haven't said this explicitly yet. Okay. So let's go ahead and return to this function right here, and let's answer these first 2 questions. When is the object to the right of its starting position? Nope.
X equals 5 to 6.
You wouldn't about the
Right,
0
it's
for the x.
Yeah, so this the object is to the right of the starting position when its s of t values are positive. They're certainly positive all through here, but our model doesn't hold there. And then they're positive from 5 onwards, but our model only goes from t equals 5 to 6. So it's moving to the right from 5 to 6. I do not include 5. How come? Because I'm at the starting position. I'm not to the right of the starting position. But I do include 6. How come? Because at t equals 6, we are to the, our s of t value is positive. We are to the right. Okay? When are we to the left of our starting position? From 0 to 5, not including either of those, because at 0 and at 5, we are at our starting position. Any questions on that, folks? Yeah, great question. We didn't check that, but notice, when t equals 0, our displacement was 0. And we got that when we put this into factored form, we saw that. Yep. So the starting position is, what is our position when time equals 0? And in this case, it is 0. Great. Other questions? Okay. This next question says, looking at the graph of s of t, when is the object moving to the right?
From 3 to 6.
So it's moving to the right from 3 to 6, says Karina. Do you agree?
Yes.
I agree. Now at 3, we're not moving to the right because what is our, well, we've said this already, but we're momentarily paused at 3. We were heading to the left before we got to 3, and after 3 we're heading to the right, but at 3 we're momentarily paused. That's reflected by our horizontal tangent line, right? But at 6, what are we doing? We're continuing to move right. The way I look at this is if you had a runner running, the model is modeling the runner running, they go past the finish line, right? So when they cross the finish line, when I stop the clock, which stops at 6 here, they are continuing to move to the right. So I would include that. They didn't come to a stop at t equals 6. Maria?
Sorry if I backtrack.
That's all right.
Question 2, though, why didn't we start at 3 again? I may have gotten lost somewhere.
For which one?
That one.
For moving to the right?
Yeah.
Excuse me, not move, it's careful, not moving to the right, but being to the right of the starting position. So let's kind of try to model this. The clock starts and my position's at 0, so here's my starting position right here at 0, the middle of the board, and I'm moving which way? To the left. How do I know that? Because my displacement's becoming more negative. Another way of saying that is the function's decreasing there. So I'm moving to the left until t equals 3. At t equals 3, I start moving to the right. Now, have I gone to the right of my starting position yet? No, not until t equals 5 have I returned to my starting position, and now I'm moving, now I am to the right of the position as well as moving to the right. So pay attention to the difference between being to the right and moving to the right. Okay? Yeah. And so then we are moving to the left from t equals 0 to t equals 3. Okay. So the next thing I ask you to do is graph v of t. I've done that. Okay. Definitely you should be able to graph all of v of t, whether you know calculus or not. From college algebra, we got the zeros at -5/3 and at 3. We know that it's a parabola, so it opens upwards. And you could even use college algebra techniques to find what we call the vertex of the parabola. Okay? If you don't know how to find the vertex of the parabola, I'm not concerned, because you could just simply take the derivative of this and find where its derivative has a horizontal tangent line. Well, the derivative of v of t, which we also call a of t, in this case would be 6t minus 4, correct? There was s prime of t, right? And so its derivative is 6t minus 4. Here's the graph of 6t minus 4. And we see that this graph crosses the t-axis at the ordered pair 2/3, 0. So where does t have a horizontal tangent line? At 2/3, whatever that comes out to be. I forget what that comes out to be. I think that's at negative 16.5, somebody told me. I'll let you double check that. So you can find the vertex either through calculus, which is the better way to do it, or if you remember your vertex formula from college algebra, where you take, for the quadratic, you take negative b over 2a. Any questions on this, folks? So we've got the graph of v of t. Using the graph of v of t, when is the object moving to the right? Well, an object is moving to the right whenever its velocity is what? Positive. When is the velocity positive? From 3 to 6. So notice that looking at the derivative, we get that we are moving to the right between 3 and 6, which is what we also got by looking at the original graph. So we can get the same information, but we look for it in different ways. If I was looking at the original function, I would say, where is the function increasing? And this function is increasing from 3 to 6. If I was looking at the derivative, I wouldn't ask where is it increasing, I'd ask where is it positive. I'm getting a couple questions. Yes?
So we're looking for where it's moving or where it's starting? Because the question was asking where it's moving.
Moving. When is the object moving to the right?
So wouldn't it be starting
The
at
vertex?
2/3?
No. What's the velocity down here? The velocity is a negative value, right?
But I was just judging it off of how we did the last one.
Yeah, but remember, the last one we were looking at the original function. Here we're looking at the function's derivative. The function's derivative tells me a lot of information. One thing it does is it tells me whether my velocity is positive or negative. At the vertex right here, what's my velocity? Negative 16.5. What does that mean? It means I'm heading which way? To the left. And it's not until t equals 3 that I'm moving to the right. Notice that that should check out. Oops. That should check out because these two answers better be the same because they're about the same object, right? So I could either ask where, so let's do that again because this is really important. I could either ask where is blue increasing, where its tangent line's positive, that's asking where is blue increasing. That happens between t equals 3 and t equals 6. That's where blue is increasing. Or I could ask where is red positive, and red is positive between 3 and 6. And they give me the same answer, but I'm looking for different bits of information. Great question. Tyler? Same question. Great. Okay. When is it moving to the left then? It's moving to the left between 0 and 3. We see that here because between 0 and 3, the velocity is what?
Negative.
Negative, so it's moving to the left.
Wouldn't the 0 be in brackets because it's still moving to the left?
Ooh,
left of that?
great question. When t equals 0, yeah, thank you. This, yeah, both of these should include 0. Folks, careful. I should have been a little more careful of that. Both of those should include 0. So this problem sort of starts. I don't start the stopwatch till I pass the start position, but I'm currently going this way. Start the stopwatch. 3 seconds. 5 seconds. Stop the stopwatch at 6 seconds, even though I'm continuing on. Yeah, great. So I should have included 0 on both of those. Great catch.
Would it also be included in the starting position one too?
Yes, so I fixed that here. Now it wouldn't be included here. I'm not to the left of the starting position yet. I'm at the starting position at t equals 0.
Okay.
Yeah. Okay. All right. Here we've graphed the velocity function. When is the velocity of the object increasing? What? So the velocity's object will be increasing. The velocity will be getting more and more positive whenever its derivative is positive. Exactly. So its velocity is increasing from 2/3 to 6. Because the velocity was getting more negative, more negative, more negative. Here's the velocity 0. Now the velocity is increasing. And so what's happening is, really you could look at this as somebody running. You started the stopwatch. They're here. Now they are speeding up, and they speed up, and they continue to speed up even through the finish line. They are picking up speed as they continue along. So much information can be gleaned from this, as far as how this person's moving or how this object's moving as it goes left to right. Think of this as somebody doing shuttle runs, right? And you picked a point in time where you started the. You guys know what shuttle runs are?
Like airport?
No. Oh, what do they call it? It was the drills you did in miserable classes. Yeah. All right. Okay. Oh. Yeah. Yeah.
No, I was gonna say, if it's increasing, the velocity is increasing at 2/3 to 6, then
Uh-huh.
why isn't it moving to the right at 2/3 to 6?
So
Because
careful.
that's a positive.
So at 2/3, yeah. So at 2/3 is so before 2/3, my velocity was negative and getting more negative. So at 2/3, I started backing up, slowing down. I started slowing down. So if I'm slowing down, what's happening to my velocity? It's becoming less negative, which is the same thing as saying it's becoming more positive. So it's at so its velocity hasn't become positive yet. It doesn't become positive until 3, but it's no longer becoming more negative.
It starts increasing.
So it starts increasing. All right, folks. I guess I want to leave it there. We'll pick up on this next time.